Everyone, we'll look at one last idea with capacitors being in series and parallel and what that does and why capacitance increases or decreases when you do the different setups. If you look at this one, these are two in parallel. That means that this plate becomes positively charged, so does this one. And that means that the bottom plates become negatively charged because they're touching the negative terminal of the battery. When you can see that if I add a third capacitor, the third capacitor is going to give you more space to put positive and negative charges on. So capacitance is going to increase because we're increasing the amount of surface area that you can pile charges onto. And that's why you can just do C1 plus C2 plus C3. More capacitance, more surface area, gives you more charge. When we're in series, remember the battery is only touching the top plate and the bottom plate. That middle plate is induced to separate its charges based on the charges they see on the top and bottom plates. So technically I could take these two middle plates that aren't touching the battery and add up their charge to be 0. So really the plates that are being charged have separated themselves by a distance d. And the further the distance increases, the capacitance decreases. And that's why when we add capacitors in series, we get a 1 over C relationship. So if that's the case for series and parallel, we could say that capacitance is proportional to area, epsilon 0 over distance. So as the area increases, we get more capacitance. As the distance increases, we decrease our capacitance. And this is what we said before. Capacitance doesn't care about the amount of charge and volts you put on it. It's just a creation of the geometry of the surface that you make. How big are the plates and how far away are those two plates? Which brings us to today's topic. If we want to pile more and more charges onto a capacitor, we've got a problem. So if we have two plates, charged positive and negative, we know an electric field gets set up between the two of them, and since there's an electric field set up between them, there's a potential and a voltage, and we know that there's an issue if this is an air-filled capacitor. If this is an air-filled capacitor, the electric field strength can't get more than 3 million volts per meter. If the electric field strength grows too strong, what you end up getting is a spark, and the air becomes a conductor. It no longer can be an insulator, and charges will jump from high to low. You don't want charges jumping from plate to plate. You'd rather those charges discharge through some device and produce some useful energy or do some work for you. What do we have to do to make this better? What we have to do is introduce dielectrics. Dielectrics are non-conducting materials that we can put in between capacitors. What do I mean by non-conductor? It's an insulator. It's plastics, it's glass, it's mica, it's paper, even gasoline could be an insulator that you could separate the two charges and slide in this insulator between the two plates to try and change our capacitance. They're going to change by this dielectric constant here. You can see kappa. Air has a kappa of 1, so an air-filled capacitor is very similar to a vacuum-filled capacitor. Has a dielectric breakdown strength of 3 kilovolts per millimeter, which is equivalent to 3 million volts per meter. But porcelain and all these other materials you can put in between two parallel plates and change the capacitance. What does that do for us? Picture A here is showing the atomic setup for the materials in an insulator. Maybe they're slightly polarized. More positive on one side, more negative on the other. If you subject them to an electric field, all of the polar molecules will shift and try to align themselves with the electric field. Positives will go to the right and negatives will go to the left. Because they become polarized, they set up their own electric field against the plates. The two charged plates set up an electric field going from left to right, and each of the little polar molecules set up its own electric field going in the opposite direction. Well, if they have their own electric fields fighting the original electric field, that means the net electric field inside the material is going to decrease. So you can see, again, picture A shows the strong electric field from left to right, and when we put that dielectric in between, it polarizes itself, separates its charges, and actually creates an electric field back against it. So what does that do? What does that mean when we put the dielectric in there? That means that our old electric field, our original electric field strength is going to change. We're going to have a new net electric field that sets up in between these two plates. And the way we can see that new electric field is it's going to decrease by a factor of kappa. So the new electric field gets weaker by this dielectric constant kappa. Alright, so our new electric field is a little bit weaker than it used to be. What does that do for us? Well, if we know our electric field drops off, let's look at our voltage. So our electric potential is electric field dotted with the displacement. So how far apart are the plates separated? Multiply by that electric field strength. Well, now we have a new electric field. So we put in our new electric field, and remember our new electric field for our new voltage is the old electric field over kappa multiplied by distance. And remember that electric field times distance is our old voltage. So really, our voltage is decreasing by the same amount. Well, let's take this one step further. With a decrease in voltage, what does that do to our capacitance? Remember, capacitance is the ratio of charge per unit volt. Well, our voltage is changing now by our old voltage divided by kappa. And if I rearrange that, since I don't like fractions, I can get charge per our old voltage multiplied by kappa. That means our new capacitance is equal to our old capacitance multiplied by this dielectric constant. So if you put anything other than air in between your capacitors, any insulator that's different than air, you're going to increase the old capacitance by whatever that factor is. So a better way of writing this full equation, the way you'll see it on the AP sheet, is you'll see capacitance is area epsilon 0 multiplied by kappa over distance. If the kappa is air or a vacuum, then it's just 1, and it's your old equation we have for capacitance. What it's doing here is it's changing the permittivity of free space. Remember, free space was pretty easy to set up electric fields. When you put an insulator in between, the electric field is harder to set up. So it changes things like voltages, and we can see it changes capacitance. So what does that do for us in terms of being connected to batteries or not connected to batteries? If we're connected to a battery, remember in our capacitance ratio, what can't change this time is the volts. The volts will stay the same potential as the battery the whole time. So if I insert a dielectric, the capacitance is going to increase, which means our charge is going to increase. Why? Now that the electric field gets weaker, the battery senses that and tries to throw more charge onto the capacitor to try and bring back the old electric field that it has. And now, since there's more charge, if you use one of your equations, let's use Q squared over C, the capacitance is increasing, but the charge is increasing by a square amount, which means that our energy goes up. Store more charge on a capacitor, you're going to have more energy available to do some work. But what happens if we're not connected to a battery? When you're not connected to a battery, remember the charge can't go anywhere. We have a fixed amount of charge on those two plates. And if we increase capacitance by throwing in a dielectric, the voltage will decrease. And if the voltage decreases, let's go back to one of our energy equations. Let's use 1/2 CV squared. We're going to see increase in capacitance, but a decrease in voltage. And the voltage is squared, so we're going to see an overall decrease in our potential energy. One thing you might be asked is, what is the bound surface charge density on the insulator that you put in there, on that dielectric? Well, since we have two parallel plates, they have a certain charge per unit area on them. The dielectric is going to have a certain amount of charge per unit area induced upon it. So if you want to solve for that, what we could do is see both of those pieces as parallel plates, and we know that uniform fields come from parallel plates. So if I want to solve for the bound electric field, it would be the bound surface charge density over epsilon 0, and the original electric field would be the surface charge density on the actual plates over epsilon 0. Remember that the original surface charge density creates an electric field to the right, and when we put in our insulator, it becomes polarized and sends its own electric field back to the left. So if I want my new electric field, or my net electric field, I can take the original electric field and subtract the bound electric field. And since we know that our new electric field is changing because of the dielectric constant in there, we could write that as the original electric field over kappa. Rearranging this, you will get that the bound electric field equals the original electric field minus the electric field divided by kappa. I can pull out the electric fields and make our equation a little bit simpler. But remember, our bound electric field and our original electric field are the surface charge density over epsilon 0, so let's replace those. And since there's an epsilon 0 on both sides, I don't need them. So since I don't need them, I could rewrite this and say that the balanced surface charge density is equal to 1 minus 1 over kappa times the original surface charge density. So we can play the if game. What happens if kappa is equal to 1? Well, if kappa is equal to 1, you get 1 over 1, or 1 minus 1, which knocks out this entire term. You get 0 times the surface charge density of the plates, which means there's nothing there. There's no dielectric. Let's go to the other extreme. Let's say that the kappa now equals infinity. If kappa equals infinity, that means this term goes to 0, and you get 1 times the surface charge density. Well, what does that mean? Well, if you get a really, really large dielectric in there, essentially what you've done is you've put in a metal. The surface charge density of the slab you slide in would be the same as the actual plates, which means you put a metal, which would not be a good idea. Remember, we're trying to separate charges, not create a conductive path. Which brings me to the last thing. Way back in electric fields, we looked at charge per unit volume, and we looked at electric fields for insulators and non-uniform scenarios. Well, this is capacitance version of doing that. We can slide a dielectric in between two plates and get a new capacitance, but what happens if you slide two separate dielectrics in there? How is that going to change your setup? Again, saying the top plate is positive and the bottom plate is negative, that sets up an electric field that points through both materials. Well, both materials will sense that and become polarized and separate charges with piling up negatives up top and positives on the bottom. And when they polarize, they'll create their own electric fields that go against the original electric field. And with these new electric fields, they're going to decrease the overall electric field between those two plates. If you look at the two dielectrics, it looks like they actually might be in parallel. The positive sides are touching the same, and so are the negative sides. So we could treat them as two capacitors in parallel. If I treat the first dielectric as a capacitor, we could call it kappa 1, area, epsilon 0 over distance, and I could see the second dielectric as kappa 2, area, epsilon 0 over distance. If you look at the picture again, the picture shows that those two dielectrics actually don't cover the entire area of the capacitor. They cover about half the area. So I've got to incorporate that into my capacitance equation. So I'm going to have to divide the areas by 2. Again, I'm going to treat those two dielectrics as two capacitors in parallel, which means all I have to do now is take C1 plus C2 to get my total equivalent capacitance between them. Summing those two capacitances together, they both have an area, an epsilon 0, a 2, and a d, so I really can just pull out kappa 1 plus kappa 2, which means all of this right here is original capacitance, so I could rewrite this as 1/2 the original capacitance, kappa 1 plus kappa 2. That would be my new equivalent capacitance. Well, since I know the capacitance, let's see if we can find the voltage. Remember, voltage is Q over C, so I'm going to take the entire equivalent capacitance and divide it by charge. So that means I'm going to flip 2D and flip the area and epsilon 0, and that leaves behind a 1 over kappa 1 plus kappa 2. That is the total voltage across our setup. But what if I want the electric field in each of the materials? Since I know the voltage is charge per capacitance, I wrote the capacitance as kappa 1 area epsilon 0 over 2D. I can write that now as voltages in each of my dielectrics. And I get this setup with the 2dQ over area epsilon 0 kappa 1 kappa 2. If I want the electric field for each, it's just voltage over displacement, the distance between the plates, and so what I get is a cancellation of the distance, and you get Q2 over area epsilon 0 kappa 1. Same thing for the electric field for the second dielectric, and since charge per area is sigma, I could write that as sigma 2 over epsilon 0 kappa 1. I would have the same thing for the second electric field, so if I wanted to find the total net electric field between those two plates with the dielectric in there, all I have to do for the second one is switch kappa 1 to kappa 2, and my new net electric field would be the original surface charge density over epsilon 0 minus 2 sigma 1 over epsilon 0 kappa 1 minus 2 sigma 2 over epsilon 0 kappa kappa 2. That's how you find the new net electric field between those two when you've got a sandwich of dielectrics in between. The book offers another example. This time the dielectrics cover the entire area of the capacitors, except now they're half as thick. So it's half the distance on each of them. So try and set this up and see how you get the total capacitance, voltage, and electric fields in each of those materials. Also, I've put a link here to Physics Girl. She explains exactly how your smartphone works. And now that you know a little bit about a capacitance, I bet you can figure it out too.